Welcome back to our YouTube channel Academic Avengers. Today, we're diving into a fascinating topic, force field, exploring its scientific roots and profound impact. In the world of science fiction, force fields are a staple. Whether it's the impenetrable shields protecting starships or the invisible barriers that keep invaders out, they captivate our imaginations. The Star Trek series often portrays scenes where Captain Kirk commands, "Shields up." A moment that has become iconic in the sci-fi genre. But what exactly is a force field? And how close are we to making these invisible shields a reality? The idea of a force field, in simple terms, is a protective barrier that can repel energy attacks, deflect objects, or block radiation. It's often depicted as an invisible yet unbreakable wall that allows those inside to remain unaffected by external threats. From energy shields in space battles to impenetrable barriers surrounding cities, force fields are depicted as essential tools for defense and survival in futuristic worlds. They appear so frequently in popular media that many wonder if such technology is even possible. However, while it sounds like something that can be built with the flick of a switch, the reality is far more complex. Despite ongoing research, creating an actual force field remains one of the most challenging feats in modern physics. The idea of deflecting bullets or missiles with an invisible barrier is still beyond our current technological capabilities. Yet, force fields remain a tantalizing concept because they represent the possibility of absolute protection, whether from weapons, radiation, or even environmental disasters. Imagine a future where force fields are not just theoretical but a practical part of everyday life. They could revolutionize various aspects of society, from military defense to urban construction. The military implications alone are staggering. Shields that could protect soldiers and equipment from attacks would change the face of warfare entirely. Beyond that, force fields could reshape industries, offering new ways to build and protect structures, regulate weather, or even contain hazardous environments like nuclear reactors. But where does this concept of force fields come from? Is it rooted purely in fiction, or does it have a basis in science? To answer that, we need to go back to the 19th century and explore the work of one of the most influential scientists in history, Michael Faraday. His groundbreaking experiments with electricity and magnetism not only changed the world but also laid the foundation for our modern understanding of force fields. To truly appreciate the significance of force fields, we must first explore the life and work of Michael Faraday, a man whose discoveries underpin much of modern physics and technology. Born into humble circumstances in 1791, Faraday grew up in a working-class family in London. His father was a blacksmith, and young Michael had little access to formal education. Despite this, his curiosity and passion for learning led him on a path that would change the world forever. Faraday's early life offered little indication that he would become one of the greatest scientific minds of his time. He began his career as an apprentice to a bookbinder at the age of 14, but his insatiable hunger for knowledge drove him to read every scientific book that came into his hands. It was through these self-guided studies that he first became fascinated with electricity and magnetism, two forces that, at the time, were still poorly understood. The turning point in Faraday's life came when he attended public lectures given by Sir Humphry Davy, one of the leading scientists of the day. Faraday took meticulous notes and even sent Davy a bound copy of his notes as a token of appreciation. Impressed by Faraday's enthusiasm and intellect, Davy offered him a job as his assistant. This was the opportunity of a lifetime for Faraday, who would now be able to work alongside one of the most respected scientists in Europe. Faraday's time working with Davy was transformative. He not only gained hands-on experience in the lab but also began conducting his own experiments. Despite being initially viewed as an outsider due to his lack of formal education, Faraday's natural talent for experimental work quickly became apparent. Over time, he earned the respect of his peers and mentors alike. Faraday's most groundbreaking discoveries came in the field of electromagnetism, particularly with the concept of force fields. His work was based on the idea that electricity and magnetism were not isolated phenomena but deeply interconnected forces that could influence the world around them. To visualize these forces, Faraday conducted a simple yet profound experiment. He placed iron filings around a magnet and observed how they aligned themselves along invisible lines of force that extended out from the magnet. This experiment revealed something remarkable. What we perceive as empty space is not empty at all. Instead, it is filled with invisible fields that can exert influence on objects within them. Faraday called these lines of force, and they represented the first clear visualization of what we now refer to as electromagnetic fields. Faraday's work showed that these force fields weren't just abstract concepts, they had real, tangible effects on the physical world. For example, by moving a magnet through a coil of wire, he demonstrated that a changing magnetic field could induce an electric current in the wire. This process, known as electromagnetic induction, was a revolutionary discovery. It laid the foundation for the development of electric generators, which would later power cities and industries around the world. Faraday's discovery of electromagnetic induction was more than just a scientific curiosity. It was a practical breakthrough that had profound implications for the future of technology. His work showed that electric and magnetic fields could be harnessed to produce energy, leading to the development of electric motors, transformers, and generators, technologies that are still in use today. In fact, nearly every form of electrical power generation used in the modern world, from coal-fired power plants to wind turbines, relies on the principles of electromagnetic induction that Faraday discovered. When you turn on a light switch or charge your phone, you are benefiting from the fruits of Faraday's labor. Faraday's influence extended far beyond his practical contributions to science. His concept of force fields had a profound impact on theoretical physics as well. Faraday's visualization of electric and magnetic fields as continuous entities that fill space would later inspire James Clerk Maxwell, who unified electricity and magnetism into a single set of equations known as Maxwell's equations. These equations not only describe how electric and magnetic fields interact but also predict the existence of electromagnetic waves, such as light itself. Maxwell's equations, in turn, paved the way for Albert Einstein's theory of general relativity, which described gravity as a force field that warps the fabric of spacetime. Einstein himself credited Faraday's work with inspiring his own ideas about how forces could be described as fields extending through space. Faraday's legacy doesn't end with electromagnetism. His concept of force fields has influenced almost every branch of physics, from quantum mechanics to cosmology. The idea that forces like electromagnetism, gravity, and even the weak and strong nuclear forces can be described as fields that permeate space has become a cornerstone of modern physics. But what about the force fields we see in science fiction? Are they purely a product of imagination, or could they one day become a reality? The answer is more complicated than it seems. While we've made significant strides in understanding and manipulating electromagnetic fields, creating a force field that can block physical objects or deflect energy weapons is still beyond our reach. However, Faraday's discoveries show us that what once seemed impossible can become reality with time and effort. Just as his experiments with electromagnetism laid the groundwork for the electric revolution, future scientists may one day find a way to create the kinds of force fields we see in science fiction. The key to such breakthroughs lies in understanding and harnessing the fundamental forces of nature. Much like Faraday did nearly 200 years ago, in the next section of our video, we'll explore the four basic forces that govern our universe, including the electromagnetic force that Faraday helped to unravel. These forces are the building blocks of everything from the stars in the sky to the technology in our hands, and they play a crucial role in our understanding of tonicity and force fields. Over the course of more than 2,000 years, one of the greatest achievements of modern physics has been the classification and identification of the four fundamental forces that govern the universe. All of these forces can be described using the concept of fields, which Faraday first proposed. Unfortunately, none of these forces possess the exact properties that we see in science fiction force fields. These forces are: the gravitational force is the silent force that keeps us grounded, preventing the Earth and stars from falling apart, and holding solar systems and galaxies together. Without gravity, we would be flung off the Earth at speeds exceeding 1,600 kilometers per hour due to the planet's rotation. However, gravity possesses characteristics that are opposite to those of fictional force fields. It is an attractive force, not a repulsive one, and it is typically weak, acting over vast astronomical distances. In other words, gravity is almost the polar opposite of the flat, impenetrable shields we see in science fiction stories and movies. For instance, it takes the entire mass of the Earth just to pull a feather to the ground, but we can overcome this gravitational pull simply by lifting the feather with one finger. In this case, the force exerted by your finger can overpower the gravitational force produced by a planet weighing 6 sextillion tons. The electromagnetic force powers our cities, giving rise to lasers, radios, televisions, electronic devices, computers, the internet, electric fields, and magnetic fields. It is perhaps the most useful force humans have harnessed. Unlike gravity, electromagnetic force can both attract and repel. However, several reasons make it unsuitable as a science fiction force field. First, it is easy to neutralize. For example, plastics and other insulating materials can easily pass through strong electric or magnetic fields. A piece of plastic can be thrown through a magnetic field without encountering any resistance. Secondly, the electromagnetic force acts over large distances, making it difficult to concentrate on a flat plane. The laws governing electromagnetic forces are described by James Clerk Maxwell's set of equations. And none of these equations yield solutions resembling fictional force fields. The strong nuclear force is what holds the nucleus of an atom together. This force is responsible for the energy output of the sun and other stars, which lights up the universe. Without it, atomic nuclei would disintegrate, and the universe as we know it would not exist. Despite its immense power, the strong nuclear force only operates over extremely short distances, confined within the nucleus of an atom. For this reason, it is impractical to manipulate or harness in the way science fiction presents force fields. Currently, the only way we can interact with the strong nuclear force is through destructive processes, such as using particle colliders to smash subatomic particles or detonating nuclear bombs to unleash the force. The weak nuclear force is responsible for radioactive decay and plays a role in heating the Earth's core through radiation. It also contributes to phenomena like volcanic eruptions, earthquakes, and continental drift. Like the strong nuclear force, the weak nuclear force acts over extremely short distances, primarily within the nucleus of atoms. Although these forces are vital to the structure and stability of matter, their short-range nature makes them difficult to harness for everyday purposes. While they are essential to nuclear physics and the behavior of atomic particles, they are far from the long-range, easily manipulated force fields portrayed in fiction. While none of the known fundamental forces meet the requirements of science fiction force fields, there is speculation that such fields may still be possible. There are two main reasons why physicists are not ruling out the possibility. First, there is the hypothesis of a fifth force that has yet to be observed in laboratory conditions. Such a force, if it exists, could act over distances ranging from a few centimeters to 0.3 meters, unlike gravity which operates over astronomical distances. However, early efforts to identify this fifth force have not yielded any conclusive results. Second, we may be able to mimic some properties of force fields using plasma, which is often referred to as the fourth state of matter. Unlike solid, liquid, or gas, plasma consists of ionized gas, where atoms are stripped of electrons, leaving behind charged particles that can be easily manipulated by electric and magnetic fields. Plasma is the most abundant state of matter in the universe, even though it's relatively rare on Earth. Stars, including our Sun, and the vast gaseous clouds floating in interstellar space are all made of plasma. On Earth, we can observe plasma in lightning and in devices like plasma TVs. The unique properties of plasma could potentially be harnessed to create force fields that resemble those depicted in science fiction. Since plasma is composed of electrically charged particles, it can be controlled with electromagnetic fields. This ability to manipulate plasma with electric and magnetic forces makes it a candidate for simulating a force field. A possible future application might involve creating a barrier of plasma, which could deflect or absorb various types of energy, like laser beams or even physical projectiles. In theory, a plasma-based shield could be powered by an electromagnetic field, allowing for an adjustable, dynamic force field. However, plasma itself is not without challenges. The high temperatures and energy required to maintain plasma make it difficult to contain. Devices like tokamaks, used in experimental fusion reactors, demonstrate how difficult it is to keep plasma confined. The intense heat produced by plasma would also pose a threat to anything nearby, potentially damaging the structures or systems it's meant to protect. Furthermore, the plasma field would need to be sustained by a constant and stable energy source, which would require significant technological advances. Additionally, while plasma can absorb or deflect certain forms of energy, it may not be as effective at blocking solid objects. The nature of plasma as a gas means it does not have the solid impenetrability of the force fields in fiction, which could stop bullets, missiles, or other physical threats. As mentioned earlier, when gas is heated to a high enough temperature to become plasma, it can be shaped and controlled using electric and magnetic fields. Plasma can be molded into various forms, such as flat sheets or windows, creating transparent barriers capable of separating two different environments. One fascinating application of plasma windows is their ability to separate air from a vacuum. In principle, plasma windows could stop air from leaking out of a spacecraft into the vacuum of space by creating an invisible yet efficient boundary between the internal and external environments. This idea is famously depicted in the Star Trek television series, where a force field is used to separate the shuttle bay from the vacuum of space. It's not only an ingenious way to save on costs but also a plausible scientific concept based on real-world physics. The concept of plasma windows was not born from science fiction but from necessity in real-world industrial applications. In 1995, physicist Audie Hershkovich from Brookhaven National Laboratory in Long Island, New York, developed the plasma window to address a problem in metal welding using electron beams. Traditional oxyacetylene torches use a stream of hot gas to melt and weld pieces of metal together, but electron beams offer a faster, cleaner, and more cost-effective welding method. However, welding with electron beams requires a vacuum environment, which was a significant challenge because this meant constructing large, vacuum-sealed chambers that were costly and cumbersome. Dr. Hershkovich's plasma window was a solution to this problem. Standing just 1 meter tall and with a diameter of less than 0.3 meters, the plasma window could heat gas up to temperatures approaching 6,650 degrees Celsius, creating a plasma held in place by electric and magnetic fields. The charged particles of the plasma exerted pressure, preventing air from flowing into the vacuum chamber, effectively isolating the vacuum from the outside atmosphere. This allowed manufacturers to use electron beam welding in a vacuum without needing massive vacuum chambers. When inert gases like argon are used in plasma windows, they emit a blue glow, resembling the iconic force field seen in Star Trek. Plasma windows, while less glamorous than the fictional fields of science fiction, represent a significant leap forward in separating two distinct environments without relying on cumbersome physical barriers. Plasma windows have been applied in various industries, especially those involving vacuum environments. For instance, in space exploration, plasma windows could be used to separate pressurized environments from the vacuum of space. Similarly, in manufacturing, processes that require vacuum environments, such as certain forms of material etching and drying, could benefit from plasma windows. These devices offer a much more convenient and cost-effective alternative to the creation of large, sealed vacuum chambers. In future space travel scenarios, plasma windows could serve as barriers to protect spacecraft or stations from sudden air leaks, thereby preventing the crew from being exposed to the vacuum of space. Imagine pressing a button to create a vacuum environment on demand. That's the kind of convenience plasma windows can offer. Now the question arises, could plasma windows be developed into impenetrable shields? Could they withstand the impact of a cannonball, for example? While plasma windows have proven useful in separating air from a vacuum, They are not invulnerable shields as portrayed in science fiction. However, with advancements in power and temperature, we can imagine plasma windows that could melt or even vaporize incoming projectiles. Yet, to construct a more practical and formidable force field akin to those seen in science fiction, we would need to combine several layers of technology. Individually, none of these technologies might be strong enough to withstand heavy bombardment, but when layered together, the resulting force field could become much more formidable. The first layer of this multi-tiered shield would be a dense plasma window, heated to extreme temperatures capable of melting metal. Plasma is known for its ability to conduct heat and energy efficiently, making it an excellent candidate for neutralizing incoming objects. In this scenario, the plasma window would serve as a first line of defense, disrupting or even vaporizing objects before they could reach their target. The second layer could be a high-energy laser grid. Imagine thousands of laser beams crisscrossing to form a mesh, which would generate enough heat to vaporize objects passing through it. This laser grid would act as a thermal barrier, turning incoming projectiles or debris into vapor before they could pass through. In addition to this, lasers can be fine-tuned to focus energy on specific points, which could be used to enhance the effectiveness of this defense layer. I'll discuss the potential of laser grids in more detail in a later chapter. Behind the laser grid, we could imagine a third layer made up of carbon nanotube mesh. Carbon nanotubes are essentially sheets of carbon atoms arranged in a hexagonal pattern, and they are among the strongest materials known to science, many times stronger than steel. Current production methods only allow for carbon nanotubes with a maximum length of 15 mm, but future advances in nanotechnology might enable us to create nanotubes of any desired length. When woven into a mesh, these carbon nanotubes could form a transparent, lightweight barrier, providing additional protection against physical objects. Since each carbon nanotube is only 1 atom thick, this mesh would be invisible yet stronger than conventional materials, offering a significant advantage for structural defenses. By combining these three layers, a plasma window, a laser grid, and a carbon nanotube mesh, we could theoretically create a nearly impenetrable wall capable of stopping most forms of attack. While this multi-layered defense system sounds impressive, it still lacks certain properties seen in fictional force fields. One of the most notable limitations is that plasma windows, laser grids, and carbon nanotube meshes are all transparent. This transparency means that while they might stop solid objects or dissipate energy from physical projectiles, they would not be effective against laser weapons. In a battle involving laser weapons, this layered shield would become ineffective because it would not block or absorb the energy from incoming laser beams. To address this, we would need to integrate an additional property known as chromatic reversal. Chromatic reversal is a concept seen in modern-day photochromic lenses. These lenses automatically darken when exposed to ultraviolet, UV, light, blocking harmful rays from passing through. The mechanism behind chromatic reversal relies on molecules that exist in at least two different states. In one state, the molecules are transparent, but when exposed to UV light, they switch to a second state, which blocks the light. In the future, we could use nanotechnology to create materials that are as strong as carbon nanotubes but can also change their optical properties when exposed to high-energy lasers. This would allow the multi-layered shield to block not only physical projectiles but also incoming laser beams, providing a more comprehensive defense. While we are still far from developing the kind of force field seen in Star Wars or Star Trek, the development of plasma windows and other cutting-edge technologies offers a glimpse of what might be possible in the future. The combination of plasma technology, laser grids, and carbon nanotubes could form the foundation of future protective barriers that are both strong and versatile. The idea of a shield that can repel physical attacks, stop high-energy laser beams, and adapt to different types of threats may sound like something out of a science fiction novel, but ongoing research into plasma and nanotechnology brings us closer to realizing this dream. Although it may take decades or even centuries, the groundwork is being laid for the development of shields and barriers that once only existed in our imagination. Do you know that science fiction is bringing the future of magnetic levitation closer? Magnetic levitation, often abbreviated as maglev, has long fascinated scientists and science fiction enthusiasts alike. The idea of objects floating and moving without any contact or friction is a hallmark of futuristic technologies in various sci-fi movies and books. These technologies often appear in the form of force fields that deflect bullets or as anti-gravity platforms that allow for the transportation of people and goods without wheels or conventional means of propulsion. One popular example is the hoverboard used by Michael J. Fox's character, Marty McFly, in the movie Back to the Future. It looked like a regular skateboard but hovered above the ground as though defying gravity itself. While such devices that negate gravitational forces remain purely fictional for now, the concept of levitating objects using magnetic fields is very much grounded in reality and science. Technologies like maglev trains already exist, using the principles of magnetism to lift and propel trains at incredible speeds. As research into superconductors progresses, the day when magnetic levitation becomes widely affordable and integrated into daily life may not be far off. This could lead to an era of flying cars, floating objects, and futuristic transportation systems once thought to belong only in the realms of fiction. At its core, magnetic levitation relies on the principle that magnets can both attract and repel each other. For instance, if you bring the north poles of two magnets close together, they will repel one another. Conversely, if you bring the south pole of one magnet near the north pole of another, they will attract each other. This fundamental interaction between magnetic poles forms the basis of levitating objects. The idea behind magnetic levitation is to utilize repulsive magnetic forces to lift an object off the ground. When strong enough, the repulsion between two magnetic poles can counteract gravity. This is the basic principle behind maglev, magnetic levitation, trains, where magnets are used to elevate the train above its track. Without physical contact between the train and the track, friction is nearly eliminated, allowing the train to glide effortlessly at much higher speeds than conventional trains. This technology is not just theoretical, it is already operational in several countries. The first commercial maglev train began operation in 1984 in the United Kingdom. It transported passengers between Birmingham International Airport and Birmingham International Station. Although this system did not operate at high speeds, it was the first practical application of maglev technology for commercial purposes. Since then, maglev trains have been built in countries like Germany, Japan, South Korea, and China, each aiming to harness the technology's potential for high-speed travel. The most famous example of a high-speed maglev system is in Shanghai, China. The Shanghai maglev train, which connects the city's Pudong International Airport to its central business district, operates at a maximum speed of 431 km per hour, 268 miles per hour. Japan has also developed maglev systems, with a maglev train in Yamanashi Prefecture reaching a record-breaking speed of 581 km per hour, 361 miles per hour, during test runs, making it faster than any conventional train in the world. These high-speed maglev trains represent the future of transportation, offering an efficient alternative to traditional rail systems. The lack of friction between the train and the track allows for greater speeds, smoother rides, and reduced maintenance costs. However, the implementation of maglev technology is far from cheap. The infrastructure required to construct maglev tracks, as well as the energy needed to power the magnetic fields, makes it one of the most expensive forms of transportation. The high costs remain a barrier to widespread adoption, though continued advancements in technology may change that in the future. The cost of maglev systems could be drastically reduced if more efficient and powerful materials were used to create the magnetic fields necessary for levitation. This is where superconductors come into play. A superconductor is a material that can conduct electricity without resistance when cooled to extremely low temperatures. The discovery of superconductors was a groundbreaking moment in physics, as it opened the door to numerous applications, including magnetic levitation. Dutch physicist Heike Onnes was the first to discover superconductivity in 1911. He observed that certain materials, when cooled to temperatures close to absolute zero, approximately -273 degrees Celsius or 0 Kelvin, exhibited zero electrical resistance. In normal conductors like copper or aluminum, electrical resistance decreases as the temperature drops. However, in superconductors, this resistance does not just decrease gradually, it vanishes entirely at a specific critical temperature. Superconductors offer two key advantages in the context of magnetic levitation. First, because they have no electrical resistance, they can carry extremely large electrical currents without any energy loss. This allows for the creation of powerful magnetic fields with minimal energy input. Second, superconductors exhibit a phenomenon known as the Meissner effect, which causes them to expel magnetic fields from their interior. When a magnet is placed above a superconductor, it levitates as though pushed up by an invisible force, due to the magnetic field lines being repelled by the superconductor. Despite the promising potential of superconductors, their practical application is hindered by the fact that they need to be cooled to extremely low temperatures to function. Cooling materials to near absolute zero requires expensive and complex cryogenic systems, making it difficult to implement superconductors on a large scale. This has led to an ongoing quest among physicists to discover materials that exhibit superconductivity at higher temperatures. Ideally, at room temperature superconductors would be a game changer. If such materials were discovered, they would enable magnetic levitation systems to be deployed widely and economically. Cars, trains, and even entire buildings could be levitated using these powerful magnetic fields. The fictional hoverboards and flying cars seen in movies like Back to the Future and Minority Report could become real technologies available for everyday use. The discovery of high-temperature superconductors in 1986 brought renewed hope to this quest. A new class of superconducting materials was found to exhibit superconductivity at temperatures as high as 90 Kelvin, approximately -183 degrees Celsius. While still far from room temperature, this was a significant leap forward and prompted a flurry of research aimed at finding even higher temperature superconductors. Today, the record for the highest temperature superconductor is held by a compound made of copper oxide, calcium, barium, thallium, and mercury. This material becomes superconducting at 138 Kelvin, -135 degrees Celsius, which is still far below room temperature but can be cooled using relatively inexpensive liquid nitrogen. Liquid nitrogen exists at 77 Kelvin and is inexpensive to produce, making it a practical cooling medium for high-temperature superconductors. However, the ultimate goal remains the discovery of a superconductor that works at room temperature. Such a breakthrough would revolutionize not only magnetic levitation but also many other fields of technology. For example, room temperature superconductors could be used to build highly efficient power grids, with electricity flowing through transmission lines without any loss of energy. One of the most exciting properties of superconductors is the Meissner effect. When a material becomes superconducting, it expels magnetic fields from its interior. If a magnet is placed near a superconductor, it creates a mirror image of itself within the superconductor. This results in a repulsive force between the magnet and the superconductor. Causing the magnet to levitate, the Meissner effect can be used to create frictionless transportation systems. For example, roads could be constructed from superconducting materials, allowing cars equipped with magnetic levitation systems to hover above the road surface. Without the need for wheels or engines, vehicles could travel at high speeds with minimal energy consumption and no mechanical wear and tear. Personal levitation devices like hoverboards or even levitating shoes could also become possible, enabling individuals to float through the air effortlessly. While superconductors are primarily used to levitate magnetic objects, magnetic levitation can also be applied to non-magnetic materials through the use of paramagnetic and diamagnetic effects. Paramagnetic materials are weakly attracted to magnetic fields, while diamagnetic materials are repelled by them. Water, for example, is diamagnetic, meaning that it can be repelled by a magnetic field. Since all living organisms are primarily composed of water, they too can be levitated using strong enough magnetic fields. In fact, scientists have already succeeded in levitating small animals, such as frogs, using magnetic fields of around 15 Tesla, which is approximately 30,000 times stronger than Earth's magnetic field. while the magnetic fields required for such feats are currently too strong for practical applications. The development of room temperature superconductors could make it easier to generate powerful magnetic fields. This would open up new possibilities for levitating not only magnetic materials but also non-magnetic ones, including living organisms. In conclusion, magnetic levitation has the potential to transform the way we live, travel, and interact with the world around us. Technologies like maglev trains are already in use today, demonstrating the feasibility of levitating objects using magnetic fields. However, the widespread adoption of magnetic levitation will depend on the discovery of more efficient materials, particularly room temperature superconductors. If room temperature superconductors are discovered, they could make levitating cars, trains, and other objects an everyday reality. The cost of magnetic levitation systems would drop dramatically, making them accessible for a wide range of applications. From floating highways to personal levitation devices, the possibilities are endless. While we are still far from achieving the vision of flying cars and hovering cities seen in science fiction, the progress being made in the field of magnetic levitation brings us closer to that reality every day. The next breakthrough could come at any time, and when it does, the world will never be the same. Thanks for watching. If you enjoyed this deep dive into the world of magnetic levitation, don't forget to like, share, and subscribe to the channel for more exciting content on the latest advancements in science and technology. See you next time.